For this lesson, we're going to be looking at the properties of graphs, and in particular the properties of graphs of functions, because that's what we're focusing on in this course. But the idea of properties of graphs are things that you've been looking at since at least grade 9 or 10, and each year we've either added on to that or we've expanded some detail in some of the things you've already looked at. Some of these are already going to be, they're going to be reviewed from you from the previous year or even past years. Domain and range, a big part of the grade 11 course, continues to be a big part of the grade 12 course. The various intercepts, that goes as far back as your grade 9 course with different focus on the meanings of the x-intercepts and the y-intercepts. Discontinuities, that's something we introduced last year. So the idea of asymptotes or holes, or if there are no discontinuities, whether or not the function is continuous. So these are all things you're going to need to be able to identify. Now, intervals of increase or decrease. You may have been introduced to these already, formally or informally, but they are going to be something you're expected to know for this course. Now, the idea of increase or decrease, I would say the single biggest item when it comes to this, the thing for students to remember is this part, the idea of always reading the graph from left to right. That is the key. So let me explain to you where people will go wrong and why you must read it this way. And let's take a look at this first change. So if you start by looking at maximums and minimums, so here is a local maximum. The temptation would be to start at this maximum and then look for intervals from there. And so you starting here, if you look backwards from here, well, this is decreasing. And if you looked forwards from here, meaning in the positive x direction, this is also decreasing. And that's where the mistake would occur. We don't want that. What we want is to always read our graph from left to right. These maxima and minima are important, but once we've identified these kind of key locations, which I've marked with these dotted lines, then we start as far left as we can on our graph, and then we start to traverse the graph in the positive x direction. Okay, so you are always going that way from left to right. So here you can see I've started this. I've got an arrow showing that I start traversing to the right, and from here it's obvious that this graph has gone up, so we have an increasing interval. Carrying on from there to the right, my graph is now decreasing. I have an interval of decrease, and then from here to the right I have an interval of increase. How we denote that, this first method of denoting an interval is something you should already be familiar with. Essentially, I'm just describing, in this case, what is this interval of increase. It occurs for all values of x that are less than -2. All values of x that are less than -2. Here, we are between -2 and +3. Between -2 and +3. That is the traditional, mathematically concise way of representing that. And now is when I'm going to point out, notice that none of these include -2. Less than -2, this one is between -2 and -3, or greater than -2, but nothing includes -2. And that's because at -2, at 3, this function is neither increasing nor decreasing. So it increases, it levels out, then it decreases, then it levels out, then it increases again. So at those points where it levels out, it's not increasing or decreasing. We don't talk about those in terms of increase or decrease. We talk about those in terms of turning points, and that's where they change from increasing to decreasing. Now, the other thing I want to point out to you is this alternate notation. This form of your notation for intervals of increase and decrease is going to become more and more common in this course and in future courses. They're both correct, but you're going to see more and more of this second notation, and at some point in time you may be actually required. There are some concepts that will actually require you to shift over to this notation. There's still ways to express it using this first notation, but you do need to be able to identify this. Now, the thing I'll just warn you about now is that this notation looks like a point. in the sense of a Cartesian point xy. Obviously that is not the case. This represents an interval, and the way you know the difference is context. If you're talking about intervals, then when you see something like this, then it's referring to an interval between -2 and 3, or between -infinity and -2. Obviously there's no confusing this one or this one with a point, because we would never represent a point using an infinity symbol. But that is a valid symbol to use when we're representing an interval. So that may be new to you, and the idea of turning points may also be new, is probably new to you. Okay, now symmetry. Again, you've probably had some discussion of symmetry, even if it was only in passing. We make use of symmetry. You may have even been introduced to symmetry when you were first introduced to quadratic equations. There are two types of symmetry that we're going to talk about: even and odd symmetry. Even symmetry is the easier one to see, and it's the easier one to show. Even symmetry occurs when you have a mirror reflection across the y-axis. So there's my y-axis, and so you can see in this case this function has a mirror image on either side of that. One is a reflection of the other. So seeing that visually is fairly straightforward for even symmetry. Algebraically, the definition of even symmetry is that f of negative x is equal to f of x. And sometimes students have a hard time, especially at the beginning, with thinking about things in the abstract here, but I just want you to understand. For example, this is the same as saying that f of -1 is the same as f of 1. There's a symmetry there. F of 1 is here, f of -1 is here, and you can see that the value of the function, the y value, is the same at both of those points. And I could change this: f of -5 is equal to f of 5, etc. Algebraically, the way we show that is it's essentially what we do as a left side, right side. So here I already have the right side. F of x is equal to x squared, x minus 2 times x plus 2. So let's calculate, or not calculate, but let's evaluate what f of negative x is. Oh, not -1, but negative x. So that just means wherever I see an x in this function, I'm going to replace it with negative x. So negative x all squared, negative x minus 2, negative x plus 2. Now, there's an elegant way of doing this, which I'll show you first, and then there's a brute force way of doing this, which I'll at least get you started on. Maybe I'll finish. Actually, I think I can show you. It's not that much trouble. But of course, we want to strive for the elegant way wherever possible in our mathematics. Negative x all squared is negative x times negative x, which is just equal to x squared. Now, the next thing I want you to do is, whenever you're doing these, whether you're doing a left side, right side check, or like a trig identity is a version of showing the left side is equal to the right side. This is not a left side, right side check. This is essentially a left side, right side proof. We're showing these two things are equal. So we are trying to get this to look like this. So I've done that in the first step already. Negative x all squared is the same as x squared. So essentially I have shown that that term is the same. That's good. I can ignore that now and focus on these other terms. Now notice that these other terms have positive x inside the bracket. So what I'm going to do is, for example, let's take this negative x minus 2. Can I write that so that it's actually a positive x inside the bracket? Well, the way that I can do that is I can factor out a -1. When I take out a -1, that negative x becomes positive x, and that -2 becomes positive 2. Now I've taken out this -1, but what I've got left behind is x plus 2. Hey, x plus 2 is actually one of the things that I wanted to show here. And again, I'll do the other one in rough as well, just over here, which is negative x plus 2. And I want a positive x in that bracket, so I factor out a -1. This negative x turns into x. This positive 2 turns into -2. And once again, x minus 2, hey, that's this term. So now let's write out what I've got, which is this first pair, -1 times x plus 2, and this second pair, -1 times x minus 2, x squared, And what is negative 1 times negative 1? Negative 1 times negative 1 is just positive 1, so I don't need to write that, it's just positive 1. And then I'm just going to change the order here. X plus 2 times x minus 2 is the same as x minus 2 times x plus 2. And I have shown, so since f of negative x is equal to f of x, therefore f of x is even. I have demonstrated that this is even. Now, what about brute force? Have you thought about how you would do that? For me, in this case, brute force would be to expand both of these fully once I've made this change and see what I end up getting. So I don't do anything subtle here like this nice factoring. Instead, I expand this. So I'm not going to do f of negative x, but let's brute force f of x. So that was our original, x squared, and then x minus 2 times x plus 2 is x squared minus 4. And then I multiply out x squared times x squared is x to the fourth. X squared times negative 4 is negative 4x squared. And I would do the same thing for f of negative x equals dot dot dot, and you would show that it turns out to be x to the fourth minus 4x squared as well, because we've already shown they're equal, so it is even. So that's an example of how to show algebraically that a function is even. To be honest with you, that's a more important skill than just being able to identify this visually. Well, if we're talking about even, then we probably need to talk about odd as well. And I don't mean odd as in strange, I mean odd as in odd numbers versus even numbers. So, odd symmetry. First of all, odd symmetry is more difficult to see in the graph because it's a rotational symmetry. So what that means, and I don't know if whether the graphics will cooperate with me here, probably not. Rotational symmetry is this. It's that idea. And actually, I guess I can kind of show it there. You can see that when I rotate this whole mess, if we just focus on the blue there, if I rotate this whole thing by 180 degrees around this central point, so I'm doing my rotation around the origin. So if we imagine rotating around by 180 degrees, we end up back at the same picture, essentially. That is an example of rotational symmetry, and when you have rotational symmetry like that, then you have odd symmetry. So that's actually a pretty tough one to see until you get the knack of it, but practice, you'll get it. Now, what about the algebra for this one? So let's take a look again like we did before. Let's take a look at 1 and negative 1. Now, I don't know what this value is. So for the sake of argument, at 1, I'm going to say that this is at negative 0.6. And that would mean that at negative 1, if this is rotationally symmetrical, if this has odd symmetry, then this would have to be at positive 0.6. Right? So we go from negative 1, positive 0.6, it rotates all the way around to here, and it then becomes positive 1, negative 0.6. If we look at those coordinates, negative 1, 0.6 has a symmetric positive 1, negative 0.6. And if you take a look, so what did we do here? We reverse the sign of the x coordinate and reverse the sign of the y coordinate. That's if we have odd symmetry. And algebraically, the way that you say that is we reverse the sign of the x coordinate here. Notice that the x coordinate is negative here, and the function itself. This doesn't mean the number is positive. This just means that the number in front, the multiplier, is positive. And then the multiplier in front of the function is negative, and in front of the x coordinate is positive. So we have, you can see here, I have positive, negative, negative, positive. There's another way that you could write this as well, which I thought I had in the note here. Or you could say f of x is equal to negative f of negative x. Again, positive, positive, negative, negative. The signs are reversed. So either of those is fine, and depending on your situation, one or the other might be useful to you. So now we're going to show that this is an odd function algebraically using that definition. Now, In this case, I'm actually going to say left side is equal to f of negative x. So, sorry, in this case it's not f, it's g. So my left side is equal to g of negative x. So I replace, wherever I see an x, I replace it with negative x. So I get negative x. This becomes negative x minus 2. This one becomes negative x plus 2. And again, we can do what we did before, all that nice elegant factoring. I'm just going to put the right side here just so we're really clear. So I'm using, there's this first definition or the second definition. I'm using the first definition here. I did g of negative x, and now I'm going to do negative g of x. That is the same as taking this whole function and just multiplying it by negative 1. And so in here I've got x times x minus 2 times x plus 2. Okay? Now, you can generally, you're always going to want to work with one side completely and then go to the other side and try to make it look the same. So we can once again be clever and do some sort of factoring here. I can take a look. I'm trying to get these two things to look like each other. And I can do that same factoring that I did before. So this negative x out front is just going to stay negative x. Negative x minus 2, I can factor out a negative 1 and turn that into an x plus 2. Negative x plus 2, I can factor out a negative 1 and turn that into positive x minus 2. So I've done that. You can see a negative 1 here and a negative 1 here. Those negative 1s become positive 1. So it's like they go away. They just become positive 1. So I am left with negative x times x plus 2 times x minus 2. And the reason why I'm targeting for this is the x plus 2 and the x minus 2, they're already here. So now, on the right side, well, negative 1 multiplied by x is simply negative x. And these other ones, this negative 1, when we make this into negative x, essentially it's used up. It's now here. And so this stays x minus 2, and this stays x plus 2. And other than a little bit of rearranging, we have the same expression. Negative x, x plus 2, x plus 2, x minus 2, x minus 2. So since left side is equal to right side, therefore g of x in this case is odd. Okay, so there's even and odd functions, working through those algebraically. End behavior. Now this is, again, this is something you've probably discussed when you were talking about asymptotes, the idea of approaching. The difference here is, here we're talking about only approaching very large positive and large negative values. In abstract terms, we represent those as the idea of going towards infinity. And you can see I've done that here. As x approaches infinity, as x approaches negative infinity, you can never reach an infinite value. That's why infinity is a more abstract value. So in this case, take a look at this graph. I'm just going to put arrows there just so you can see that that continues. I have a horizontal asymptote here. So as, I guess the scale does not show up. Oh, we're going to deal with that here using the equation actually. We'll figure some things out. As x approaches infinity, what does y do? So as x approaches infinity, well, that's a very large value for x. So if I kept going to the right here, what would happen to this y value? It would continue to go up and up and up and up. So as x approaches infinity, y approaches infinity. That's our answer here. And that infinity can be a positive or negative infinity. As x approaches negative infinity, what is this y value doing? And as you can see, as x approaches negative infinity, this y value is approaching the asymptote. So we need to know what the value of that asymptote is. And if you remember your exponential functions, Normally the asymptote is along the x-axis at y equals 0, but this one has been shifted down by 3. So this is actually the line y equals negative 3. So as x approaches negative infinity, my y value approaches, it is not equal to, that would be incorrect to say equals, it approaches negative 3. And that's an example of end behavior, and that's how you would express it. You would just use the word as. If you said, just if you didn't have the word as there, I would understand what you meant, but poor form, you need to put something in front to express that you are looking at end behavior. Obviously, once you put these arrows in here, context would tell me what you mean. Make sure you don't put in equal signs. And that's it. And there's also a handout to go along with this one. Make sure you do these questions in the order that's recommended here.